Started with the nervous system. Today's session is mainly about the embryological development of the nervous system. But what I would do is I would start with a little bit of an introduction on the organization of the nervous system so that you have some idea of what we are talking about. And then this is not going to be a detailed session on the embryological development. This is an introductory session. So you would have some idea of how the brain develops. But the major session on the development of the brain would come at the end when you have done everything. So this is an introduction session on the development. We are going to talk about a little bit on the organization of the nervous system, and then we are going to move forward. Okay? So as we know, the nervous system is divided into two parts. One is the central nervous system and the other is the peripheral nervous system. The central nervous system includes the brain and the spinal cord. Okay? So brain and the spinal cord constitute the central nervous system. The nerves which are coming out are going to give rise to the peripheral nervous system. So the nerves which are coming out from the spinal cord, these are the spinal nerves. The ones which are going to come out from the brainstem, they are called the cranial nerves. The cranial nerves are going to supply the head and neck region. The spinal nerves are going to supply everything below the head and neck. So everything below the head and neck is supplied by spinal nerves. Everything in the head and neck region is supplied by cranial nerves. There are 12 pairs of cranial nerves and there are 31 pairs of the spinal nerves. Also, in the peripheral nervous system, you can include parts of the autonomic nervous system. So the nerves which are going to supply your viscera are parts of the autonomic nervous system. But part of the autonomic nervous system also will come in within the central nervous system. So part of your parasympathetic and sympathetic nervous system, which is the nerves supplying these organs, is a part of the peripheral nervous system. The rest of it is going to be the part of the central nervous system. Now, within the brain, you can have three parts of the brain. The first one is the cerebrum, which is the highest center of the brain. So that is going to control everything. And when we are going to say the functions of the brain, we are always going to talk about motor function, sensory function, higher mental functions. So these are the three things which you are going to see whenever you are going to talk about the brain or the nervous system. Motor function, sensory function, higher mental function. So what do you mean by motor function? Any movement. So that is your motor function. Sensory function could be general sensations like pain, temperature, touch, fine touch, vibration, proprioception. All these are general sensations. Then you have special senses like hearing, like balance, like smell, taste, vision. Okay, so you have sensory sensations which could be classified as general and special, while you have motor activity, and then you have higher mental functions like memory, language, cognition. So whenever you are going to test the function of the brain, you are going to do a sensory examination, motor examination, higher mental function examination. So these are the three ways how you are going to test the brain. Most of this course, you are dealing with either motor function or sensory function. Later half of this course, you are going to deal with the higher mental functions. But most of it is either motor or sensory or combined, motor and sensory. And mostly when you learn about the brain, we have learned about the brain mostly by damaging different structures. So we cut something and then see what is lost. Sensory, motor, autonomic, whatever. So you need to learn the function of the brain and the structure of the brain in the same way, the way we have learned it, by cutting different parts of it. Okay? So the next part of the brain which is important is the cerebellum. And cerebellum is a small part of the brain which is lying below the main cortex. It looks like a smaller piece of the cerebrum. The major function of this is a coordinator. So what it does, it takes the sensory input from the body, matches it with the intended motor activity, and then see what is the difference, and then send corrective signals back to the cerebrum. So when you are moving or you are picking up this, I placed it this, and I have an intention to pick this up, the sensory information is being sent, and my intended movement is also being sent to the cerebellum. And cerebellum is sending corrective signals while I'm picking up this object. So if the cerebellum is not right, I might go forward, or I might undershoot and would not be able to pick up this. Similarly, it is related with all the things, like your balance. So correction of your balance, correction of your movements, correction of any motor activity is the function of cerebellum. So cerebellum is not responsible for starting any activity. Cerebellum is not responsible for any sensory information, sensory recognition. But what it does is it's comparing the sensory input with the motor input and then send corrective signals during the real-time movement. So it is important in coordination. Then we come to the brainstem. We said all the sensory inputs have to go to the cerebrum. All the motor activity has to come, directives have to come from the higher center, which is the cerebrum. So it has to pass from somewhere. So the part of the brain these are passing is the brainstem, and then into the spinal cord to supply the lower part of the body. So both spinal cord and the brainstem are acting as conduits to allow the sensory input to go up and the motor fibers to go down. So one function of the brainstem is to allow these fibers, sensory and motor fibers, to pass through. The other thing is that the brainstem is supplying the head and neck region. So the motor activity in the head and neck region is supplied by the neurons which are present in the brainstem. The motor activity in the rest of the body is supplied by the spinal cord. So if you have an injury, you have a trauma patient coming in, and the motor loss or sensory loss is only below the head and neck region, most probably it is spinal cord. If it is in the head and neck region, then it would be mainly brainstem. So when you only see any motor or sensory losses in the head and neck region, it's mainly brainstem, because brainstem is the one which is supplying the head and neck region. All the cranial nerves are going to come out from the brainstem except the first two, the olfactory and the optic. So olfaction and visual sense are not going to the brainstem. All the rest of your sensory inputs from the head and neck region are all going to the brainstem. Okay? Brainstem also has some very important autonomic functions, like controlling the heart rate, controlling your respiratory rate. So if the brainstem is damaged, you might end up in cardiac arrest and respiratory arrest. So cardiac centers and respiratory centers are also present in the brainstem. So that's why brainstem is important. Let's look at the structure of the brain. You see, this is the cerebrum. Can you make out? This is a sagittal section of the brain. So we have cut the brain into half, and you're seeing one half of the brain. There is another half exactly similar on the other side. So what you're seeing here is this is the cerebrum. And so this is the right cerebral hemisphere, there is a left cerebral hemisphere. There are lobes in this cerebrum, frontal, parietal, and then you can see the occipital temporal lobe is just seen here. So this is the temporal lobe of the cerebrum, frontal, parietal, and occipital. You can see a white matter bundle here. Can you make out this? This is the corpus callosum. You are also going to see this septum, which is actually separating a cavity which is inside the cerebrum. There is a cavity inside the cerebrum which you are not seeing here, because you are seeing a septum which is separating this cavity. The cavity inside the cerebrum is called the lateral ventricle, because you have two cerebral hemispheres, so you have two cavities. These cavities are called lateral ventricle. If you see just below the septum, this is the septum pellucidum, which is separating the cavity. Just below the septum you can see a hole. Can you make out this hole?
Yes.
This hole is the foramen of Monro, or the interventricular foramen. This is opening the lateral ventricles into a cavity of the between the thalami. So this is the thalamus, number 17. There are two thalami. Between the two thalami there is a slit-like opening which is called the third ventricle. So the two lateral ventricles, which are the cavity of the cerebrum, they are opening into a slit-like opening between the two thalami, and that is called the third ventricle. And from the third ventricle, this is the brain stem. Number 9 is the medulla. Number 15 is the pons. And number 10 is the midbrain. The cavity of the midbrain is aqueduct of Sylvius, or the, cerebral aqueduct. Cerebral aqueduct or aqueduct of Sylvius. This is communicating the third ventricle through the aqueduct of Sylvius into this cavity, which is the fourth ventricle. The fourth ventricle is the cavity behind the pons and medulla, and it is roofed by the cerebellum. So cerebellum is forming the roof, and the floor of the fourth ventricle is formed by the pons and medulla. So aqueduct of Sylvius is opening into the fourth ventricle, and fourth ventricle is continuing down as the central canal of the spinal cord. Now, these are the cavities inside the brain. They are producing the CSF, the cerebrospinal fluid. So CSF is produced in the lateral ventricle, it is produced in the third ventricle, it is produced in the fourth ventricle. But the fluid is inside the brain. It needs to come out and cover the brain and the spinal cord. So in the roof of the fourth ventricle, there are certain openings which bring the CSF out, and then it is circulated around the brain and the spinal cord in the subarachnoid space. Why it moves up and down? Because in the subarachnoid space you have the major blood vessels of the brain, and when they pulsate, they move the CSF around or circulate the CSF around the brain. Why am I talking about all this? Because when we are going to talk about the development, we need to see the cavity, these fourth ventricle and the lateral ventricle, they are coming out from which part of the neurotube. So we are going to talk about it as we are going to talk about the development. Okay? So just have we are going to have a detailed talk on the ventricles and the CSF circulation, but just to give you an introduction, where the CSF is produced, what is lateral ventricle, what is third ventricle, what is the fourth ventricle, you should have some idea about it. Okay? Clear? Any confusions, please let me know.
What's number 16?
Number 16 is the temporal lobe of the cerebrum. You are just seeing it from the medial side, so if you see from the lateral side, you would see the temporal lobe. So this is the temporal lobe of the cerebrum. Make out these. Can you make out these parts? I hope this is easy. Okay, now we are coming to the embryological development of the brain. So, as you know, the brain starts to develop around the third week of development. And if you see this picture, you can see, if we take the the amnion out. So you are seeing a slipper-shaped ectoderm. Can you make out this? A slipper-shaped ectoderm. This is the surface ectoderm, which is looking like a slipper. You have taken the amnion out. You're looking at the embryo from the top. So you have taken the amniotic cavity out and you're looking at it from the top. This is around the 3rd week of development that you start to have the neural plate developing. So the surface ectoderm in the center over the top of the notochord starts to infold. And as it starts to infold, it is going to give rise to the neural folds. Okay? So over the top of the notochord, the surface ectoderm starts to infold, giving rise to the neural folds. And this is around the 3rd week of development. You can see it much better here. This is the notochord, and you can see the surface ectoderm starts to fold, giving rise to the neural folds. And then the middle piece of the neural tube, neural folds, is going to get detached from the surface ectoderm, giving rise to the neural tube. Only the cells on the edge are going to get separated, giving rise to the neural crus cells. So what is happening here? The surface ectoderm, which was here over the top of the notochord, it starts to fold, and then it gets detached from the surface ectoderm, giving rise to a tube, which is called the neural tube. The edges of these neural tube are also going to get separated, giving rise to the neural crest cells. Now, as this neural tube is going to be formed, the cranial end and the caudal end of this neural tube will still remain open into the amniotic cavity. And these are called the cranial neuropore and the caudal neuropore. So cranial neuropore is the cranial end of the neural tube, which still will remain open into the amniotic cavity. Similarly, the caudal end of the neural tube is going to still remain open into the amniotic cavity, giving rise to cranial and caudal neuropores. So you have the cranial neuropore going to close around the 25th day of into the amniotic cavity. Similarly, the caudal end of the neural tube is going to still remain open into the amniotic cavity, giving rise to cranial and caudal neuropores. So you have the cranial neuropore going to close around the 25th day of development, or the 20th somite stage. So around the 20th somite stage or 25th day of development, the cranial neuropore, which is the cranial end of the neural tube, is going to close, and 2 days later the caudal neuropore is also going to close. But sometimes, you have neural tube defects and you do not have the closure of the cranial neuropore, or you do not have the closure of the caudal neuropore. So that leads to neural tube defects. So that's why you need to know there is a cranial neuropore and there is a caudal neuropore. Non-fusion of cranial neuropore or the caudal neuropore will lead to neural tube defects. You can see it here. This is the neural tube forming. Initially you have, this is the cranial neuropore and the caudal neuropore. This is also, you can see the cranial neuropore and the caudal neuropore, and then they are going to fuse, giving rise to a single neural tube. Now once the neural tube is formed, it is going to give rise to 3 vesicles, 3 bulgings. So there would be prosencephalon, mesencephalon, and rhombencephalon. Prosencephalon is called forebrain, mesencephalon is the midbrain, and rhombencephalon is the hindbrain. So there are 3 vesicles which you can see: forebrain, midbrain, and hindbrain, or prosencephalon, mesencephalon, and rhombencephalon. There are 2 flexures which are going to develop. So there are 3 vesicles, 3 bulgings: prosencephalon, mesencephalon, and rhombencephalon. And the later part is going to give rise to the spinal cord. and there are two flexures. The first one is called the cephalic flexure, which you see here. The cephalic flexure is between prosencephalon and the mesencephalon. So this tube was like this. Now it is going to bend like this. So as it is going to bend, it is going to be the bend between the mesencephalon and prosencephalon. This is the cervical flexure. The other flexure is between the rhombencephalon and the spinal cord, and this is called the cervical flexure. So you have two flexures and three bulgings. Prosencephalon, mesencephalon, and rhombencephalon. There is a cephalic flexure and there is a cervical flexure. The cephalic flexure is between prosencephalon and mesencephalon, and cervical flexure is between rhombencephalon and the spinal cord. You understand this, everybody? No problems. Okay. By the fifth week of development, what would happen is that this prosencephalon, which was the forebrain, it is going to give rise to two outpouchings. So this was a single vesicle. It is going to give rise to two vesicles laterally, and these two lateral vesicles or two outpouchings which are going to come out, they are called telencephalon. They are going to give rise to the cerebrum. They are going to give rise to cerebrum. So the two cerebral hemispheres are going to come out from telencephalon. The central part of the prosencephalon is going to give rise to diencephalon, and diencephalon is going to give rise to the thalamus and hypothalamus. From the diencephalon, you would have an optic vesicles coming out, which is going to give rise to the optic nerve and the retina. So the optic nerve and the retina are the outpouchings from the diencephalon. Do you understand this, everybody? So prosencephalon was one vesicle. It gave two outpouchings which are called telencephalon. They are going to give rise to the cerebrum. The central part is called the diencephalon, which gives rise to thalamus and hypothalamus. And then you have from the diencephalon outpocketings, which are called the optic vesicles. They are going to give rise to the optic tracts and the retina. So now you are seeing here in this picture, you see this vesicle which is coming out from the prosencephalon. This is the telencephalon. The central part is the diencephalon. Then the rhombencephalon, which was one vesicle, is going to have this isthmus or a division, a constriction, which is called the rhombencephalic isthmus. The rhombencephalic isthmus is going to divide the rhombencephalon into an upper part which is called metencephalon and the lower part which is called the myelencephalon. The metencephalon, which is the upper part of the rhombencephalon, is going to give rise to pons and cerebellum, while the myelencephalon is going to give rise to the midbrain. Medulla. So medulla oblongata is going to come out from myelencephalon. Metencephalon is going to give rise to the pons and cerebellum. Now you can see another flexure here. Can you make out this flexure? A bend forward. This is called the pontine flexure. So the first flexure which we talked about was the cephalic flexure, which was between the mesencephalon and prosencephalon. Then we talked about the cervical flexure, which was between the rhombencephalon and the spinal cord. And this is the pontine flexure, which is between the metencephalon and myelencephalon. And there is a constriction here which is called the rhombencephalic isthmus, which is dividing the upper part and the lower part of the rhombencephalon. The upper part is called the metencephalon, which is going to give rise to the pons and cerebellum. The lower part is giving rise to the medulla oblongata. Now, as we said, you see this neural tube is a hollow tube. Neural tube is a hollow tube. So there is a cavity of telencephalon is a vesicle. So there is a cavity inside it. So the cavity of the telencephalon is what? Lateral ventricle. The lateral ventricles are the cavities of telencephalon. The cavity of the diencephalon is third ventricle. The cavity of mesencephalon is aqueduct of Sylvius. The cavity of the median and myelencephalon is fourth ventricle. And then the cavity of the spinal cord is the central canal of the spinal cord. So you can see that the vesicles have a cavity, and that cavity is relating to the cavities of the brain. So initially, this is a hollow tube. There is a single line of epithelium which is lining this hollow tube. Later on, cells are going to come in as from these, the epithelial lining, which is going to reduce the size of these cavities. Initially, the size of the cavity is large. There is only one single line of cells which is lining the tube. As the cells are going to differentiate, they are going to compress the cavity, and then you would have a smaller cavity as you see in the adult brain. There is more tissue, cavity is small. Okay? So now we are going to see how these cells are formed, the neurons and the other cells which are formed in the nervous system. So if you see the lining of the cavity, it is lined by neuroepithelial cells. And neuroepithelial cells are pseudostratified columnar epithelium. So the neural tube is lined by pseudostratified columnar epithelium, and this is called the neuroepithelial cells. They are called what? Neuroepithelial cells. These neuroepithelial cells are going to give rise to neurons, and they are going to give rise to the glial cells. So glial cells, which you see in the nervous system, and the neurons in the nervous system, which are the main type of cells in the nervous system, they are all going to get arise from the neuroepithelial cells, and neuroepithelial cells are the ones which are lining the neural tube. Clear? So all cells in the nervous system are coming out from the neuroepithelial cells, and these neuroepithelial cells are lining the neural tube. They are pseudostratified columnar epithelium. Clear? Now what we are going to talk about is only the development of the spinal cord. So we are not going to talk about the rest of the development of midbrain, medulla, pons, cerebrum, because once we dealt with all that, then we are going to talk about their development in the later half of this course. But we are going to deal today about the development of the spinal cord, which is much more easier to understand. Okay? Okay. So spinal cord also is formed by the caudal part of the neural tube. So the caudal part of the neural tube is going to give rise to the spinal cord. It is lined by these neuroepithelial cells. So the neuroepithelial cells are lining the caudal half of the spinal cord. What happens later, that from these neuroepithelial cells, there are specialized type of cells which are going to differentiate and move out from the neuroepithelial layer into a layer surrounding the neuroepithelium. And this layer surrounding the neuroepithelium is called the mental layer. It's called what? The mental layer. The cells which are going to migrate there, they are called the neuroblast. And neuroblast are circular cells with a central nuclei. So from the pseudostratified columnar epithelium, you would have cells which are called the neuroblast. They are going to migrate around the neuroepithelial cells, giving rise to this layer which is called the mental layer. And they are consist of neuroblast. The collection of neurons in the floor piece, because neural tube initially is like this. So there is a floor and there is a roof. So the floor part of this neural tube, the collection of neurons here are going to form a plate which is called the basal plate, while there would be collection of neurons in the roof part of this neural tube, and they are going to give rise to the alar plate. The basal plate, in the adult spinal cord, you have seen the gray matter which is called the anterior gray horn cells. So basal plate is going to give rise to the anterior gray horn cells, which are primarily motor neurons. The alar plates are going to give rise to the posterior gray horn cells, which are primarily sensory neurons. Then outside the mental layer, you have another area which you can see here. This is called the marginal layer. This marginal layer is going to be formed by the processes of the neuroblasts, which are going to extend into the marginal layer. The axons of the neuroblast, as they are going to differentiate, they are going to give rise to the marginal layer. So if you see the adult spinal cord, there's a central canal, there's the anterior gray matter, the posterior gray matter, and then you have the white matter. So gray matter is coming from basal and alar plate, and white matter is coming from the marginal layer. Okay? And the central piece is going to give rise to, as the cells are going to expand, this central neural tube canal is going to reduce in size, giving rise to the central canal. And then these neuroepithelial cells which you see here are going to differentiate into ependymal cells. You understand this? Everybody is with me or not? Okay. So after the neuroepithelial cells are going to differentiate into neuroblast and glial cells, glioblast, they are going to, after they give rise to neuroblast and the glioblast, they are going to differentiate into ependymal cells. So final differentiation is ependymal cells. So basal plate is going to give rise to the motor neurons, the anterior gray horn cells. The alar plates are going to give rise to the sensory neurons, because these are the posterior gray horn cells. Yes, go ahead. Yes, mental layer would have two collections, one in the floor piece, which is called the basal plate, and one in the roof part, which is called the alar plate. In the roof part, you would have the sensory neurons. In the floor piece or the anterior part, you have the motor neurons, okay, which are coming from the basal plate. So basal plates are going to give rise to motor neurons. The alar plates are going to give rise to sensory neurons. Now this is showing you the histogenesis. So initially you have a neuroblast, which is like this, which is coming from the neuroepithelial cells. Then it is going to develop processes and it will become bipolar. So now it has one process here and one process here. So it has become a bipolar neuron. And then it is going to develop the dendrites and the axon, and this is the shape of the mature neuron. So from neuroepithelial cells, you would have a neuroblast, bipolar, and then a multipolar neuron. So this is how they are going to differentiate into different types of cells. You also know that we talked about the neural crest cells, that when the neural tube was forming, piece of the edges of the neural tubes are going to get separated and going to give rise to neural crest cells. Neural crest cells are going to give rise to the dorsal root ganglia. So there are 31 dorsal root ganglia all around the spinal cord. These are the primary cells where you have the sensory neurons. So neural crest cells are the ones which are going to give rise to the dorsal root ganglia. Now from the dorsal root ganglia, you would have neurons which have two processes, one moving towards the periphery, one moving towards the spinal cord. So the part which is moving, the axonal processes of the neural cells in the dorsal root ganglia, which move into the spinal cord, they are going to synapse with the neurons inside the alar plates. So they are going to synapse with the sensory neurons of the alar plate, while the peripheral process is going to join with the peripheral processes of the neurons in the basal plate to give rise to the spinal nerve. So spinal nerve has both sensory and motor component. Sensory component coming from the dorsal root ganglia, and the motor component is coming from the basal plate. The processes of the basal plate are going to join there, giving rise to the the motor component of the spinal nerve. So spinal nerve is a mixed nerve. It has a sensory and a motor component. Now, besides neurons, we also have supporting cells in the brain and the central nervous system, and these supporting cells are called glial cells. There are 4 or 5 major types of the glial cells. One are the astrocytes. Astrocytes are similar to the rest of the body like fibroblasts. So the fibroblast in the rest of the body, the connective tissue, you have in the brain no fibroblasts, but you have these glial cells which are called astrocytes. The other type of glial cells which are present in the central nervous system are called oligodendroglaya, and oligodendroglaya are important in myelination of the neurons in the central nervous system. And the third type of cells are the ependymal cells which line the ventricular cavity. One of the glial cells are called microglia, and these are the phagocytes of the brain, and they are the only cells which do not come out from the neuroepithelial cells. So neuroepithelial cells are going to give rise to the neurons. They are going to give rise to all the glial cells. So they first transform into glioblast, and glioblasts are going to give rise to oligodendroglaya and astrocytes, and after they differentiate into the glioblast and the neuroblast, the neuroepithelial cells are going to transform into the ependymal cells which are lining the ventricular cavity. But the microglia are the only cells which do not come out directly from the glioblast. They come out from the mesenchymal cells. They are the mesenchymal cells. They migrate with the blood vessels to the brain, and these mesenchymal cells are going to differentiate into microglia, and microglia are the phagocytes of the brain. We are going to talk about these cells in more detail tomorrow, that what is the function of the astrocytes and the protoplasmic astrocyte and the fibrillar astrocytes or glioblast or whatever. But you should know that all the glial cells are going to arise from the neuroepithelial cells except microglia, which are the phagocytes of the brain. We have talked about neural crest cells. We said that neural crest cells are important in the formation of the dorsal root ganglia, the neurons in the dorsal root ganglia. They also are important in giving rise to the Schwann cells. The Schwann cells are the cells which myelinate the peripheral nerves. So in the central nervous system, myelination is done by the oligodendroglaya, which are arising from the neuroepithelial cells through the glioblast. But Schwann cells which myelinate the peripheral nervous system, they arise from the neural crest cells. Neural crest cells are also important in giving rise to the sympathetic ganglion, and they are also important in the formation of the medulla of the suprarenal gland. And the last thing which they do is that they are important in giving rise to a special type of cells in your skin which are called melanocytes. So the pigment cells inside your skin, the melanocytes, also come from the neural crest cells. So neural crest cells are important in giving rise to the dorsal root ganglia, the sympathetic ganglia, the medulla of the adrenal gland. They are important in giving rise to Schwann cells, and they are important in giving rise to the melanocytes, which are the pigment cells in your skin. Okay. Next is the positioning of the spinal cord, which is important. You know that the spinal cord in the initial part of the development of the embryo is going to run throughout the vertebral column. So in the initial part of the development of the spinal cord is going to run throughout the vertebral column. So from foramen magnum till the coccyx, you would have the spinal cord. But as the later half of the development of the embryo goes in, the vertebral column expands much more faster as compared to the spinal cord. So at birth, the spinal cord is till the L3 vertebral level. So below the L3 there is no spinal cord. The spinal nerves, although, would have to travel all the way down to their vertebral level and then exit out. During the adult life, you would have the spinal cord at the disc between L1 and L2. So the vertebral column even is going to extend more faster, and the spinal cord is going to end at L1 and L2. So what would happen? The nerves still would have to go down and exit at their particular vertebral level. So if you see the spinal cord, it is going to end at L1, and below that you would see a bunch of nerves going down and then exiting out at their particular level. So it looks like a horse tail. Below the termination of the spinal cord, you would look like a horse tail of nerves going down. That's why it is called cauda equina. That means cord means tail, equina means horse. So below the termination of the spinal cord, you would see a bunch of nerves going down, exiting out at their particular vertebral level. Do you understand this? So this is an important concept. The other thing is the meninges, which are covering the spinal cord, they are going to extend to S2 vertebral level. So your subarachnoid space is still below the spinal cord. You would have subarachnoid space because the meninges are going to continue all the way up to the S2. Or the spinal cord is going to end at L1, L2, but the meninges are going to extend till the level of S2. So your subarachnoid space is also going to extend till the level of S2. In terms of the molecular relationship of the spinal cord, there's a lot of detail given here. What you need to remember are two important regulators. One is the TGF-beta and the other is the sonic hedgehog. So the quantities of the TGF-beta and sonic hedgehog are important, because in the floor piece of the spinal cord, you have high quantities of sonic hedgehog, while in the roof piece of the spinal cord, you have high quantities of TGF-beta. And these quantities will determine the formation of the basal plate and alar plate. The basal plate are motor neurons, alar plates are sensory neurons. So wherever you would have high quantity of TGF-beta, you would start to have genes expressed which will allow the formation of alar plates. Wherever you have high quantity of sonic hedgehog, you would have the expression of genes which will result in the formation of basal plates, which are the motor neurons. So the two important regulators which you need to remember is sonic hedgehog and the other is the TGF-beta. One is for the sensory neurons, the other is for motor neurons. So determination of their quantities is going to result in the formation of alar and basal plates.
So the roof piece will have more
beta. Okay. Next we are going to talk about the condition which is called the neural tube defect, which because this is one of the most common type of defects which you are going to see. It is because of the abnormal closure of the neural folds in the 3rd and the 4th week of development. So the exposure of the teratogens during the early pregnancy can lead to neural tube defects. These abnormalities can result in neural tube defects, may involve the meninges, vertebra, muscles and skin. So it's not only the spinal cord, the coverings around the spinal cord and the brain could be affected. So it could be the vertebrae, the skull bones, the meninges, the muscles, all could be affected because the closure of the neural tube is going to induce the closure of the vertebral arch. It is going to induce the muscle formation and all those things. So what you need to know that abnormal closure of the neural tube can result in defects surrounding it. Severe entities involves the neural and non-neural structures and approximately occurs in 1 into 1000 births. But in certain areas like northern China, it is very prevalent, and you can have 1 in 100 birds to have neural tube defects. So although it is a common condition, certain areas are endemic, where you would find a lot of neural tube defects. Now, the most common type of neural tube defect is called the spina bifida occulta. This is the defect. It's called the spina bifida occulta. Occulta means that you don't see anything. So what is happening is that the vertebral arch is not formed, and there is no protrusion of the spinal cord or the meninges. The only thing which you will see is a tuft of hair and a dimpling around the lumbosacral region, especially in the S2 region. So if you see a tuft of hair coming out and a depressed portion, it's a spina bifida occulta. There is no meninges, no part of the spinal cord which is bulging out. The more severe form of the spina bifida is the spina bifida cystica, and it could be, with the cystica you can have the bulging of meninges, and you could have the bulging of meninges with the part of the spinal cord coming out. If it is the meninges only, it's called the meningocele. If it is the part of the spinal cord and the meninges, then it is called meningomyelocele. Now with the occulta, you have no motor defect, there is no sensory defect. So everything is normal, only thing is the tuft of hair and the dimpling which is coming out, which is there. The rest, there is no sensory defect and there is no motor defect. But with the spina bifida cystica, the meninges coming out or the part of the spinal cord coming out, you might have variable sensory motor defects in the lower limbs, and they might have problems with urination, or you might have problems with defecation. So you need to know that spina bifida cystica can be with meningocele and it can be with meningomyelocele, and it would have some sort of variable sensory and motor defects which you can find in the child. More severe form of the spina bifida is something where you have no vertebral arch, there is no skin, no meninges covering, and the spinal cord tissue or the nervous tissue is exposed to the exterior. There is no skin, no meninges, no covering, and the spinal tissue is basically exposed to the exterior. This is called rhexis. So rhexis is the condition. It's a very severe form of the neural tube defect where you have no covering of the skin, there is no covering of the meninges, and the nervous tissue is exposed to the exterior. Similar to what you have learned in the GI system, where you have gastrochesis. If you remember, gastrochesis, the intestines are outside without any covering. Similarly, in rhexis, the nervous tissue is exposed to outside without meninges, without any skin covering, nothing. Okay? It's a type of neural tube defect. Now, sometimes you have with the neural tube defects, a spina bifida cystica, you can also have hydrocephalus. Now, why you can have hydrocephalus? You remember that we said that the vertebral column extends much more faster than the spinal cord. If you have spina bifida cystica and part of the nervous tissue is attached to the vertebra, what would happen as the vertebral column is going to expand faster? It is going to pull down the brain down, and as it is going to pull the brain down, part of the cerebellum is going to pass through the foramen magnum, and this will compress the cerebellum against the medulla, compressing the openings in the roof of the fourth ventricle. So the CSF cannot come out into the subarachnoid space, leading to accumulation of the CSF within the ventricular cavity, and that condition is called hydrocephalus. So hydrocephalus can happen with the spina bifida cystica because of the tethering of the spinal cord with the vertebral column, and as the vertebral column is going to expand, it is going to pull the brain down through the foramen magnum, obstructing the openings in the roof of the fourth ventricle, so that the CSF starts to accumulate into the ventricular cavity, giving rise to the hydrocephalus. This condition where you have spina bifida cystica and hydrocephalus, this is called the Arnold-Chiari malformation. It's called Arnold-Chiari malformation. You can see the spina bifida cystica by doing an prenatal ultrasound. So if you are doing a prenatal ultrasound around 14th to 16th week, you can actually see the spina bifida cystica, and you can also determine the alpha-4 fetoprotein level in the maternal blood and the amniotic fluid. That is also diagnostic for diagnosing spina bifida cystica prenatally. That means before birth. You can diagnose spina bifida cystica by doing a prenatal ultrasound or by determining the levels of the alpha-fetoprotein in maternal blood and in the amniotic fluid. We can correct the spina bifida cystica in utero by doing a surgery around 28th week of gestation. So you don't have to correct this condition after birth only. You can correct this condition in utero around 28th week of development. Hyperthermia, valproic acid, hypervitaminosis A produces the NTDs. That means women who are taking retinoic acid for acne, they should not take, if they are planning to become pregnant, they should stop taking any retinoic acid, which is vitamin A, for curing the acne. People who are epileptic, they need to be changed from valproic acid to other types of anti-epileptic drugs. Hyperthermia also can cause neural tube defects. So these are the major causes of the neural tube defects: hypervitaminosis A, valproic acid, hyperthermia. Acne is one of the most important conditions which you should remember. Most women take retinoic acid for preventing the acne, so that need to be stopped if you want to get pregnant. And 70% of NTDs can be prevented by just giving 400 micrograms of folic acid. So you can have these pills if you are becoming pregnant. This is going to help you in not developing NTD in 70% of patients. Thank you very much.